sponsored by the Lee Company. Lee Company minimizes size and maximize performance with their fluid control technology engineered specifically for aerospace applications. The company's passion for innovation enables it to solve their customers' toughest challenges. And a commitment to cutting-edge manufacturing processes and unmatched quality is the reason why industry leaders have continuously relied on the Lee Company in mission-critical applications for over 75 years. The finalist for this category is Sentry, a software-defined passive sensor for counter-stealth and battlefield survivability. And here to present the idea all the way from Denmark, and sorry if I don't pronounce this correctly, but Robert Merck and Sten Schmidl. I got hopefully that right, but he can correct it. So welcome.
Just grab it. Thank you for having us. It's been a great honor, and it has been a really interesting process. My name is Robert. Sten is over here. I've spent 25 years in the military, and I've served both within the major warfare areas and the combat rescue community. We are dividing this up a bit, so I'll start out and talking about the number one problem or number one issue within those areas is first of all the find task, whether or not you're talking about an enemy or if you're talking about an isolated person that you need to rescue somewhere. Most of all is usually in the contested areas, the find task will be even more difficult. And therefore we are having a now weather-independent application for this find task. So without further ado, strap in because Sten is one of the quickest, the most cleverest person I've known. So he will take it away from here.
I'll try to do my best, Robert. So thank you very much. And okay, so what I'm going to tell you is basically how we would like to use well-known technology that we have been researching for the past 2 decades at university level into a completely new context. We already know how that we can map the world using passive radiometers. We apply Planck's radiation law, and we basically build a radio receiver, and then we can characterize our planet. We can do that in many ways. We can measure the Gulf current by measuring the sea surface salinity. We can measure the soil moisture. We can measure wildfires. We can measure droughts. We can measure a whole bunch of things using radiometers. And it has been well known to scientists for the past 50 years, and they have been using this technology from space during the past 45 years. But over the past 2 decades, we have a new threat against our science, and that threat is coming from ourselves as human beings because we demand more and more bandwidth. And what we see here is actually the threats that we are up against. So in the upper right corner, we see how television satellites contaminate the measurements from the sea surface, how the measurements over great land surfaces is contaminated by active radio sources and at many, many different frequencies. So it narrows in our possibility to make science. So what we as a scientists have been doing is that we have developed new technologies to actually detect the interference and remove it. And we already have running processors applied for satellites. We have one satellite in space already applying the technology, and we have many upcoming in the years to come. Over here on the right, we see one of our prototype radiometers that is being flown on various aircraft in Denmark and in many other countries, also already applying the technology. But with one and only purpose, we would like to detect interference. And what we are doing is that we apply a modern technology in order to look into the statistics of what we are actually measuring. Because to keep things in a simple way, nature is chaotic, it's random, and what humans do is usually not. So we can separate those things, and we can actually see human activity down to 100s, or in many cases even down to 1,000s of the level of the natural radiation. So we can also look into the polarization of radio signals. Again, humans are organized, nature is not, and we can do that at the spectral level, at a timing level, so we have many tricks in order to separate what humans are doing and what nature is doing. And the point is, humans do emit radio signals. They have to switch on the smallest electronic device, and we would know that because we need to know that, otherwise as scientists we would produce wrong results. So go build a camp in the Arctic somewhere, think you are hiding yourself, switch on a GPS receiver, and we'll spot you. Because what the scientists would be doing, they would say, oh, that was unfortunate, that data point is contaminated, so we better throw it away. What Robert and I would be saying is, oh, give us that data point and let us know more about it, because then we can maybe even tell you what they switched on. Because there's actually a potential for classification of sources. Scientists also already know how to characterize the different matter they find on exoplanets. How are they doing that? By looking into the emission spectrum. What would we be doing? We would be looking into the emission spectrum of electronic devices. Then we can tell you what they switched on. What kind of vehicle did they switch on? What kind of GPS receiver did they switch on? Is that a Russian one? Is it a Chinese one? Or is it an American one? That would be good to know. And technology is there. We have operational satellites already in space, throwing away valuable data points every day because scientists can't use them. They say, okay, jolly good, give them to us. We have the upcoming ESA mission called SIMMER. It's a multiband. It's a multiband mission that's supposed to be launched within a very few years. They even have further ideas. The Cryosat mission that is being proposed for the Earth Explorer 12 program would be an extremely wideband radiometer receiving background radiation and throwing away a lot of valuable data point. Robert and I know what to do with them. So satellites produce data all the time. We can apply that technology for something useful. Maybe we can point out that, say, within 10 by 10 kilometers, we can find something. Okay, let us build a system that we can put on a drone. Then we can maybe tell you within 10 by 10 meters where the target is. So what would you do about that, Robert?
Thank you very much. I hope you just got at least a bit of it. We are talking about several applications for this, and I'm sorry to say for the judges that, for example, the B-2 stealth bomber would also radiate something about that. So we have a anti-stealth capability in this. And for soldier safety, we will also have the opportunity to look into a passive sensor that might be working in conjunction with radar, which is an active sensor. As a rescue in rescue situations, we will have, for example, on Iceland, in mountain ranges, in the vast ranges in the U.S. or in the icy currents of the Bering Strait, you would be able to pinpoint people much faster than you could right now, because you can see through cloud and the bad weather. You can do that from a distance. That will also mean that you would eliminate the risk for the rescue people. You would eliminate the risk for the person in trouble, because they would be rescued a lot faster. So less time on station for the rescue community, and more time or a quicker find would increase the survivability of all parties. And if you're looking into, as you said, the profiles of signatures, when you start collecting a lot of this data, then we will be able to go into to cataloging and setting up profiles for each and every single transmission. So, and the transmission data would be different, or the transmission profile would be different from, for example, a T-72 or T-80 tank. So you'd even be able to look into how you can categorize those from a distance. I don't want to get into antenna theory, but and again, Steen can do a lot more about that. We are currently in a position where the only thing we need is more capability and more manpower to work on this project. Right now, it's us two, and we are currently looking into hiring a PhD on this event also. So the more effort we put into it, the faster it goes. But since it's a small company with only limited resources, we of course are working as fast as we can to get into this. Pending your questions, that was the presentation. Thank you.
Judges, questions? We'll start from the back.
You mentioned an awful lot of uses for this in the geospatial regime and size distance. Are there any that can be used on smaller areas, such as I'm thinking of even an oil, gas, petrochemical plant that would help to monitor some of the local activity on that size scale?
Yeah, the issue is, again, looking into antenna theory, that you can put any antenna at any size on whatever carrier you have. So you would also be able to, for example, put it on ships, which can carry a bigger antenna, and then you would be able to spot aircraft and other stuff flying around. But the more stationary a platform you have, the bigger the antenna without any risk to it. Right now, as Steen said, since it's measuring currents, the antenna on the satellites have very high resolution. So we're looking into very big pixels. But if we can do that with putting, for example, on a drone, we could even hover in a very, very low distance, and we could also even use it for mine clearing and something like that.
Next question.
So the way I understand it is it can make use of existing sensors, like you had all the satellite examples. That hinges on you getting access to the data. I mean, obviously that's a question. And the combination is like a synthetic aperture or like a very large array or interferometric. I'm not quite sure how you get the resolution, how you get the ground or the sea surface without interference of the surface.
Yeah, I think we need to see the solution twofold. First, getting access to the data. The satellites that applies this kind of data nowadays is mainly civil available data. So that means you can go to the homepage of ESA or NASA and download the data. You will just see that warning flag, don't use this data point for any scientific use because it's contaminated. So that's basically where we will start. But where I see the real potential and what I see the idea that our PhD students should investigate is actually to get a system up running similar to the prototype that I showed a photograph of and get that up running either in a stationary field setup or actually building a version that is capable to fit on a drone. And there's nothing in technology that wouldn't make it fit onto a drone. So, I mean, you can build it into a matchbox and you can still make it work. And that's where I see the scalability, that you use the satellite to point out, say, you have some activity into a 10 by 10 kilometer space in Arctic, then you launch your drone into that area and investigate in details where is actually that activity. But that's what we need that's what we need the PhD student for. But from a technological point of view, there would be no obstacles because we use the well-known technology already existing.
Is there a possibility to, for military purposes, could they create a simulated signature?
Just to make sure I understand your question correctly, so you think if they would be able to create a signature that would spoof our system in a way so that we would think they have some activity there? And
like we could have a B-2 bomber, but it could put out a signature of a 747 or an MD-11, right? If they deliberately tried to create that signature.
In a sense, they could, but they still need to hide what they already emit. And if they try to, say, create a stronger signature to, like, overrule the natural signal coming from the bomber itself, so then they would, in a sense, try to spoof us, but we will see that the signal is unnaturally large, and then we will see that something suspicious is going on there.
Okay. And one other question related to that. So if you know what your signature is there a possibility of generating an inverse of that to try and cancel it out?
Well, theoretically, you can always cancel a signal out. The problem seen from you as the user of any electronic device would be that what you cause of a noise signal would be something that you are typically not in control of, because if you would be in control of, then you wouldn't emit it anyway. So it might be theoretically possibly to think of mathematically cancelling out the signal, but since you don't know what you are emitting until you already did so, then it would be difficult for you to counteract it.
One last question.
I have a question. Is this on? Yeah. All right. Thank you. Yeah, with regards to both the stealth and counter stealth comments you had up there, I mean, your radiometer produces some signal, so which is then detectable. So how do you get around that in a say a stealth aircraft?
Again, just to make sure I understand your question correctly, so our radiometer is a passive receiver, so we are in a sense only emitting what we are not in control of, and we should not be emitting anything, otherwise we would reveal ourselves, but we are not emitting any signal like a radar does. So that's a major difference between a radiometer and a radar, that we are basically only receiving. So if we emit anything, it's only because we have not shielded ourselves carefully enough, exactly as the emitters that we are going to try to detect. But we are a passive sensor, so that was just to make sure I understood the question correctly.
Okay. Yeah, you did. I didn't quite understand that. It was purely passive sensor.
Yeah, it's a purely passive sensor, that's true.
Okay.
Great. Thank you. Thank you.